Have you ever stopped to think about the massive, invisible world right beneath your feet? Seriously, right now there are hundreds, maybe even thousands of miles of pipes crisscrossing under your city, carrying everything from water to waste. It's a system we absolutely rely on, but what happens when a piece of it, buried deep underground, breaks? I mean, how do you even begin to fix something you can't see?
So let's start right there with the problem itself, because this is a huge challenge that pretty much every city on the planet has to deal with.
So, let's get right into it. When a pipe cracks or a joint starts to leak, what are your options? For decades, the answer was, well, it was messy, it was expensive, and it was incredibly disruptive.
Yeah, the traditional method really only meant one thing: digging. Bringing in all the heavy machinery, tearing up roads, rerouting traffic for days, sometimes weeks, and just creating a ton of noise and dust. It's a total brute force approach. Sure, it fixes the pipe, but it causes a whole new set of problems for anyone living or working nearby.
But what if you didn't have to dig? Thankfully, engineering has come up with this brilliant, almost surgical solution that avoids all that chaos. It actually fixes the pipe from the inside out. It's called Cured in Place Pipe, or CIPP for short, and the concept is just incredible. Instead of digging up the old, broken pipe, engineers feed a soft, flexible liner that's been soaked into special resin right into it. Once it's in position, they cure it using heat or light, and that resin hardens. And just like that, you have a brand new, seamless, super strong pipe right inside the old one. No digging required. Now, CIPP isn't a one-size-fits-all kind of fix. Sometimes you do need to reline a whole city block's worth of pipe. But what if the problem is just one single crack? A tiny leak in a pipe that's otherwise perfectly fine? Well, that's where things get really smart.
So this tech gives engineers two main options. They can do a full length lining, which is kind of like a complete remodel for a long section of pipe, or they can use what's called a point repair, a precision strike with a super strong patch that's applied only to the exact point of failure. It's faster, it's way more targeted, and it's often a lot more cost-effective.
And the process itself is just so elegant. First, a little robotic CCTV camera goes into the pipe to find the exact location and see how bad the damage is. Then, a resin-soaked sleeve is pushed or pulled right into place, directly over that defect. Finally, it's cured, often in as little as 30 minutes, and it hardens into a permanent structural repair. It's a fix that's measured in inches, not city blocks.
But you might be thinking, how can such a small patch really be strong enough to hold? Well, the secret isn't just in the process, but in the really advanced materials they're using.
This quote from the source material just nails it. A point repair isn't just covering a hole. It has to be strong enough to literally bridge that weak spot and carry all the weight and pressure from the soil and traffic above completely on its own. It's basically an engineered bridge, just on a very, very small scale.
And to really get how strong these patches are, just look at the numbers. A standard liner can handle around 4,500 pounds per square inch. But the material for a point repair, that needs to withstand at least 6,500 psi. That's more than 40% stronger, and it has to be because it's handling all that external stress in one very concentrated spot.
So what gives it that incredible strength? It's the reinforcement. Instead of a simple felt material, these point repairs use a special fiberglass reinforced woven fabric. Think of it like the rebar you see in concrete. That fiberglass provides immense strength, allowing a really thin patch to be far stronger than a much thicker, unreinforced one.
Okay, but the fabric is only half the story. The resin, the glue that hardens to form the patch, is also critically important, and engineers choose the resin based on the specific job. Polyester is kind of the cost-effective workhorse. Vinylester is what you'd use for pipes in more corrosive industrial environments. And then there's epoxy. That's the top-tier choice, offering the absolute maximum strength for the most critical situations.
So we've got a super strong material and a high-performance resin, but putting it all together correctly isn't just a matter of slapping it on. Oh no, it's a very precise engineering calculation.
How thick does a patch really need to be? Well, it depends. But for larger pipes, this number is key. A thickness of just 6 millimeters is often the minimum you need to provide enough structural integrity to last for decades. Just 6 millimeters?
And that thickness isn't a guess, it's calculated based on real-world conditions. Engineers have to account for everything: the weight of the soil and traffic pressing down from above, how deep the pipe is, the pressure from any groundwater trying to crush it, and of course the diameter of the pipe itself. All these things go into the final design of that little patch. And here's the beautiful result of all that engineering.
Because that fiberglass material is so incredibly strong, the patch can be remarkably thin, and that means it creates a powerful repair without significantly reducing the inside diameter of the pipe. It keeps everything flowing efficiently.
Okay, we've gone through the problem, the technology, the engineering, but let's bring this all back to the surface. Why does this invisible fix actually matter in our daily lives?
Well, it means your commute isn't ruined by a giant hole in the road. It means repairs that used to take weeks can now be done in a few hours. It saves our city's money by fixing only what's broken. It results in a stronger, more durable pipe that's going to last for another 50 years. And really, it all adds up to smarter, more resilient, and more sustainable infrastructure for every single one of us.
This kind of targeted, high-tech solution has totally transformed how we maintain this hidden world of pipes. And it kind of leaves us with a final question, right? What other invisible systems that we rely on every single day are just out there, waiting for their own revolutionary fix?